Hello CIO world, and welcome to another installment of Chemical Engineering Design. In this lecture, we will be going over external forced convection. In the study theme, we will cover the following. Firstly, we'll be distinguishing between what constitutes internal and external flows, followed by the differences between frictional drag and pressure drag. And also, we will go over how to perform calculations that pertain to the convective heat transfer coefficient under various flow regimes across flat plates. And also across cylinders, as this will become more important in the design of shell and tube heat exchangers. So let's get right into it and first go over what we mean by internal and external flows. Internal flows occur when the fluid is completely surrounded by and interacts with a solid confinement, like inside a pipe. External flow is different in that it is not completely confined and so does not interact completely with a solid interface. These differences will, of course, have an impact on the phenomenon such as frictional effects, the friction coefficient, the development of the velocity and temperature profiles, of course, and therefore also how heat is transferred through these two flow cases. For the case of internal flows, we often apply a resistance to the pipe entrances as a Kr factor, and also to pipe exits. And this reason becomes apparent when you plot the pressure against the length of pipe as shown here. What typically happens is that the flow, as it enters the pipe, there is a marked non-linear pressure drop at the entrance, and then once flow is fully developed inside the pipe, then the pressure drop becomes more linear and then can be described quite easily using the Weisbach equation that we have in any case been applying to piping system design. Now, the entrance length is defined as that part of the pipe in which the flow is still developing, and the pressure drop is of course non-linear. And obviously we can't accurately determine the pressure drop using the Darcy-Weisbach equation alone, so we've been adding things like the resistance coefficient in the resistance coefficient method, Kr, to account for the associated pressure drops when dealing with pipe entrances as well as pipe exits. Now, for a fluid that is confined in a pipe, the flow characteristics are developed faster than for the same fluid that flows over an external flat plate. Obviously, there's less interactions for the fluid. So therefore, we would need to define specific equations that will describe these differences in the flow, where we have already described these equations for piping. Right, so the main focus for us is on defining the drag force and then relating these entities, the pressure and the frictional drag force, to the drag coefficient CD, which is obviously the same as F prime in the case of pipes. But we also focus on heat transfer, of course. So how do we determine Nusselt number, Reynolds number, etc. Now, drag occurs due to two main physical interactions of the fluids with its surroundings, namely frictional drag, which is due to shear stresses that are experienced by the fluid flowing across a solid surface, and also pressure drag due to the onset of a pressure gradient that is induced for the fluid that, in the presence of some solid surface, but it's based on the solid surface's orientation. So look at the differences shown here in terms of the two sets of figures. How do these different drag phenomena arise? So in the case of frictional drag, flow is tangential to the surface, while the pressure drag is generating this drag due to the flow being normal to the solid surface. Okay, now as we have defined the drag coefficient before with the following equation, which is just another version of the Darcy-Weisbach equation. Okay, so we've been using the Darcy-Weisbach equation in piping system design. We can also have a similar equation for the case of flat plates. So here where we have CD, we've been using the friction factor, which is F prime for piping system design. So notice how the pressure drop in this equation is actually split into its two components, namely the drag force FD, as well as the surface geometry A, and the remaining terms rho and V squared are together divided by 2, the dynamic pressure for the system. So in other words, we use the same form of equation to describe pressure drops for fluids across the surfaces, okay? And it just so happens that for pipelines, we just include the FD over A in that term delta PF prime. Okay. Right, so flow across the surfaces of flat plates also have defined flow regimes. Now with pipes, we would typically have laminar flow regime throughout, or transitional flow throughout, or turbulence flow. But have a look at this picture and you'll see that the flow regimes actually change as you go across the surface, from the leading edge on the left through to the main surface of the flat plate, and as you leave it, you tend to leave with the flow being turbulent. Okay. And as with piping, we also use a few equations then to determine the friction factor, F prime or CD, based on the flow regime. And in the prescribed textbook, you will find the following equations, which may be used to determine the friction coefficient with the respective range of Reynolds numbers for which they apply. And for very rough surfaces, the following equation may also be used. It's kind of like when we use the von Karman equation when we have fully rough developed flow regimes in pipelines. Right, and notice that this equation, for instance, is a function of the absolute roughness epsilon and the length L. Now similarly, we have also a set of equations for the Nusselt number. Okay, and this also depends on the flow regime. And recall that we can also use the definition of the local Nusselt number or the average Nusselt number at a position x distance from the leading edge, or for the entire length, if you're working with the average Nusselt number, to determine the convection coefficient H. Okay, because that is what is important for heat transfer. We want to know how is convection taking place. For conduction, it's easy. We have a thermal conductivity. For convection, it's a little harder. We want to know how do we determine H, because for chemical engineering design, process dynamics, process control, flow often changes, okay, because of disturbances and also because of changes in set point. And so we have to be able to know how does the convective heat transfer change. So the following equations then apply for the determination of the Nusselt number across a flat plate, which depends on both the flow regime and obviously the fluid's Prandtl number. And then these are then also useful for determining the heat transfer coefficient, which is actually what we are really after. Now always remember to check these equations in the textbook. There are going to be quite a lot of them. Check what conditions apply to these equations. Make sure you know where to find the Prandtl number. If you have a textbook or are given an equation, just make sure to determine this first. There are also other equations that apply to specific cases for fluids, such as liquids and also those of metals. Okay. Or for liquids whose Reynolds number multiplied by the Prandtl number is larger than 100. And let us now pay attention and pay humble respects for yet another dimensionless number that was discovered by the discoverer, Peclet, which is named after him, the Peclet number, which is defined by the other two dimensionless numbers of Reynolds number and Prandtl number. Congratulations, give that man a buzz, and much celebrations. To end off our discussion on heat transfer for flat plates, we will focus our attention on how heat is typically transferred. Okay, so this is for flat plates. Now, firstly, from the leading edge where the fluid is starting to interact with the flat plate, the convective heat transfer coefficient gradually decreases due to the development of the laminar flow boundary. The laminar profile obviously creates a barrier for heat transfer, since the laminae that develop prevent mixing and thus convection to take place easily in the y direction. Now, with the onset of turbulence, due to the mixing that takes place, there's obviously going to be a sharp increase in the convective heat transfer coefficient, and again with the development of the turbulent boundary layer as it grows in the y direction, this will have a negative effect on the convective heat transfer as the coefficient will steadily decrease again. Now, in the design of heat exchange equipment such as plate and frame heat exchangers, it may not be that the whole flat plate participates or interacts for heat transfer or with respect to heat transfer. So let's consider the example where at some distance zeta no heat is being transferred to or from the fluid. Then the following equations would apply for calculating the Nusselt number, and likewise there are also two sets of equations for determining the convective heat transfer coefficient as is shown. In the case where there is a uniform heat flux, okay, so the previous equations were for isothermal flux, isothermal temperature. If you have instead a uniform heat flux throughout the length of pipe, the following equations apply, where instead of you having an isothermal temperature given to you throughout, the rate of heat transfer is given instead with the surface temperature Ts, and obviously Ts will change due to changes in heat, the convective heat transfer coefficient. And you must think about the cases where this will become important. When will you have isothermal temperature being experienced, such as at the reflux drum of a distillation column? Where will you have constant rate of heat flux, such as off of a heating element, for example? Now, the last case that we want to get into is for external forced convection that will entail flow across cylinders as well as for spheres. Why spheres? Well, sometimes we have a reactor, chemical reactor, where we have flow that goes past spherical catalyst beads or larger beads of a graphite encased uranium. And also cylinders, well, because shell and tube heat exchangers are designed based on pipes. So let's first have a look at the case for the sphere. So in the spherical case, notice that with spheres we get the typical vortex shedding into the wake region behind the sphere. How this shedding occurs is a function of flow, specifically the Reynolds number. And for lower Reynolds numbers, in the region of about 15,000, the angle at which these vortices are shed occurs at about 80 degrees, as measured from the face of the sphere. So think of the face as if you were going to punch the sphere in the same direction of flow. That is the face that we're talking about. Now, for higher Reynolds numbers, double of 30,000, this shedding occurs closer to the back of the sphere at an angle of 140 degrees. What is important to notice is that the wake decreases with an increase in Reynolds number, and this will become important because the wake and the drag go hand in hand. So it should be noted that both friction and pressure drag occurs, but the friction drag is more dominant at the lower Reynolds number, and that the pressure drag, which is tangential, is more dominant at higher Reynolds numbers. Now, since the friction factor is affected by both the surface morphology of the solid interface and the Reynolds number, changes of these two parameters can be used to change how and when vortex shedding will occur, and obviously this will have an impact on heat transfer. But in other cases, if you are interested in aeronautical engineering, it will interfere with how planes fly, how golf balls fly, things like that. Okay, so notice how the friction coefficient slightly increases up until a certain Reynolds number is reached, and then declines steeply with increases in Reynolds number. Also note that by increasing the relative roughness, epsilon over d, it is possible to shift this sudden reduction in the friction coefficient to the left, so that it occurs at lower Reynolds numbers and therefore at lower flows, because the diameter is obviously going to remain the same, and the fluid properties, viscosity and density, also remain the same, more or less. So this is exactly why golf balls are designed with small dimples on their surfaces. Okay, so this means that the golf ball, with its higher relative roughness, can experience much lower drag forces at the typical speeds that are obtained when you hit a golf ball into the air, and if you do it correctly. The result is that the golf ball can travel much further than it would have if the surface was completely smooth. This is mostly due to a reduction in this wake that we were talking about, which is responsible for that pressure drag that the golf ball would experience as it flies through the air. But this is not always good news. Once flow reaches very high turbulences, the boundary layer that forms becomes thinner and thinner, and it can so happen that a very rough surface may begin to experience very high drag forces, frictional drag forces, and due to these frictional forces that are created by the rough surface, we have obviously higher friction factor that we end up with. Okay, so much more friction is experienced. Now, of course, since there are different regional characteristics of flow across the surface of a sphere, there will also be differences in the Nusselt number, depending on whether you are in front or at the back of the sphere, and also likewise the convective heat transfer coefficient. So firstly, consider the change in the angle for the wake development, at what angle it starts to develop, how this would contribute, such that there are two distinct regions for the Nusselt number as it develops. Okay, so for low Reynolds numbers, the Nusselt number decreases and then does so quite sharply at specific Reynolds numbers, while for very high Reynolds numbers, the Nusselt number will first decrease, okay, and then you'll have this very sharp increase, and then there will be a kind of a recovery. You'll have a drop again, and then you'll kind of stabilize. Okay, so just compare the Reynolds numbers, because obviously you have different flow regimes that are interfering with the development of the boundary layer. Right, so a similar phenomena also occurs in the case of cylinders, as shown here, because cylinders also have the cylindrical profile that a sphere has, and each geometry yet again will have its own specific equation to determine the Nusselt number. Now it should be noted that here with the first equation, this is only applicable for single cylinders, and that these two equations only apply to smooth surface geometries. It should also be remembered with all of these, also with internal convection and external convection, when you are determining Nusselt number, Reynolds number, etc., you must determine the fluid properties at the film temperature, which is the average between the surface temperature and the bulk temperature, Ts plus T infinity multiplied by a half. Okay, so just keep that in mind. Now the textbook does provide additional cases for differences in geometries, flow regimes, as well as the fluid type. So you can go over those yourself. Now what we as chemical engineers are most interested in is the multiple cylinders, since these are used in the design of our beloved heat exchange heat exchangers that we refer to as shell and tube heat exchangers. So lots of different pipes that are surrounded by a shell. Okay, now two main types of packing are typically used in industry for the design of these shell and tube heat exchangers. They are namely the inline and the staggered tube profiles. Now again, pay attention to the specific requirements when making use of these equations. Okay, so just make sure that you read the textbook very carefully and see that you use the right equation for the right application. And with that, we end off this discussion of the external forced convection. See you all next time.